Yeah, so I'm still so wait, this is not working. How about now? Okay. Um, yeah, so I'm still
Oh, my bad.
okay, anyway, I was just saying I'm still so fresh that I haven't found all of my USB sticks in my boxes yet. Okay. Um, all good? Okay. I know it's always hard to do technical stuff when you're not like here every day. Um, so I grew up in Michigan, so I understand your cloud problem. I grew up in a really small town in a blue collar family, and I was always a radio astronomer, or sorry, I was always an amateur astronomer. Some of my earliest memories are of me being like 5 or 6 and getting in trouble for wandering out in the backyard at night. Um, and then I upgraded to telescopes. In high school, I used my Celestron 5, sorry, the Celestron Nexstar 5, to do a project with a solar filter monitoring sunspots. That let me get to the International Science Fair. I just like worked my way up in the levels. And then I think that let little redneck me get into the University of Michigan, and that really set me off on the astronomy path. So I got a special spot in my heart for um yeah for amateur astronomy. Sorry, it's been a long day and I'm probably over caffeinated right now. Um, anyway, but with my sunspot project, so I'm a high school student that has to monitor sunspots, which I can only do between like 3:30 and 5 p.m. in the fall semester in Michigan. I did that project with 7 data points, but I did it. And that was over a 6-week period. I was collecting data every day I tried. And that actually leads me into my next point is that coincidentally, not only do I love star formation, I'm also a radio astronomer. How do I next?
Page down.
Oh, that's weird. Okay. It's okay. We'll make it work. Because of my trauma with the clouds, yes. This dude. Yeah, I love students. They're the best. See, they look at this stuff every day. They know. Yeah, so because of my trauma with my high school science fair project and the clouds, when I finally got into radio astronomy, it was absolutely because you can look through the clouds with the radio telescopes. You can observe during the day. It doesn't matter. It's amazing. In a really heavy cloud cover, depending on your wavelength, maybe you can't use that. But the longer and longer wavelength you go to, the more transparent the atmosphere is. It's awesome, and I feel like a wizard when I'm working on data and pulling out cool new science using all of my methods and programming and whatever. And then, but I'm pulling that out from like data that was taken during the day during really cloudy conditions. And I'm just like, ooh, other people don't get to do this. It's only for radio astronomy. So that's a little advertisement for you. Go. Okay. So that brings me to the types of light. Like, I still like the other types of light. We learn different things at each frequency. So I like using this galaxy example. So here is visible. I mean, you all know what galaxy looks like. You're space fans. It's the typical spiral arms. You can see that there's these dark, dusty lanes. There's the glow in the center near the supermassive black hole where everything is much hotter and warmer there. But then if you move to radio, you actually see that at the center, there's a complete hole. What? But we just said that there was a black hole in there. But that's not the black hole, don't worry. But we said there was a black hole in there and that there was a ton of material that's really hot. So how come in radio there's nothing there? That's because this radio image is actually showing us the dust in that galaxy. So we can actually see that in the center, probably everything was so chaotic, so hot that the dust grains have been completely destroyed. Dust can't live in the center of the galaxy. That's why there's a hole. This gets blasted away. And then in infrared, you sort of see this loop, this circle here, this ellipse, where the dusty radio light is really bright, is exactly where you see there's like, oh, I fixed it. You see the super bright, or sorry, you see the super dark area exactly corresponding to the areas where it was super bright in the dust. And there is infrared light in here, or that originates in there, but it doesn't make it out of the galaxy. It gets absorbed by all of that dust that we can see in the radio. So the brightest areas with the dust in the radio image are going to be the dimmest parts in the infrared. That also means that they're complementary. So what the radio image can't see in the center, the infrared can. And in that really dense, dusty area, that torus or donut out there, we can see that in the radio. So multi-wavelength observations are the way to go. And just, I won't go into details here, but you can also see that, again, ultraviolet and X-ray show you completely different features as well. The more wavelengths you get, the more science you can do. I still like radio astronomy the best. And this is just like a little schematic. I like to pull this up when I'm thinking about, is the telescope I'm going to be using, should it be on Earth or down on the ground? So here in the visible, I mean, we see stuff with our visible sensitive eyes. So we know we can see visible light down here. But then radio waves has a huge bandwidth that we can be using. It's amazing. If you go too far, it gets opaque again, but there's this magic area right in here. I love it. Best part of the spectrum. Of course, we have the infrared, which we don't observe too much from the ground because the atmosphere is super opaque here. So that's why we sent JWST to space. Uh-oh. Maybe I should update this slide because that's a drawing of Spitzer, which is, a previous generation, but it did good. So, we're going to give it some props. And then if you get into the really highly energetic photon range down here with like gamma rays, ultraviolet, X-rays, and once again, you have to go into space. So where you send your telescopes completely depends on where you can actually see it. If you can see it from the ground, nobody's going to give you funding to build a telescope in space. So that's why we still have ground-based facilities. This is my favorite radio telescope. It's the largest radio telescope in the world in terms of collecting area, but not dish size. So there are some telescopes out there, like there's the FAST telescope, which is one that's sort of built into a basin in China. That telescope is massive, like it's multiple football fields across, but there's only one dish. However, this telescope has 43 12-meter wide antennas that are all connected together, sent through a supercomputer, and then they wind up getting processed so we can actually see the images. But these antennas, the further apart you spread them, the higher resolution images you can make. And unlike that one radio telescope that's a few football fields across, the largest separation you can have with these antennas is 16 kilometers. We are seeing fine detail. Depending on the distance to your source, we're able to resolve 1 to 5 AU resolution detail, meaning we can start examining solar systems that are ours, which I guess solar means sun, so forming planetary systems. Yeah, but this is the Atacama large millimeter sub-millimeter array. This is absolutely my favorite telescope. It's down in Chile. I haven't been down there to visit yet, but I hope one day I can. And this is at, I believe, 14 kilometers in elevation. It's really high, and you have to pass an altitude fitness test, so I might have to hit the YMCA first. Okay, so I just want to do a little brief aside with some schematics, and then we'll get back to the pretty pictures. But I just want to explain why radio astronomy is actually really complicated, and there's a lot of mathematics under the hood. So we're going to pretend that instead of 43 antennas, we just have 2 for this purpose. But if you have your target star here, and you have waves of light that are coming in, if you get it parallel to your dishes, everything goes great for a while. But since the dishes are so far apart, when this wave hits along this plane, it's going to hit this antenna first, but this one that's farther away still has this path length still to travel. So when the light hits the antennas, they're all going to be out of phase. How do we fix this? Because if you can't line up the observations in time just perfectly and then correct for that path length difference, you're just going to get garbage. You're not going to get science. So the solution is you pass the information that comes from the antennas into pretty much a supercomputer, but we call it a correlator because we're very demure, we're very mindful. And then in the supercomputer, what we do is we mix a local oscillator frequency. So we inject an artificial signal that we know the exact profile and properties of. So then we dig back into the data, find the signal from each antenna, and we can align it that way. And then we send it through about 30 steps of algorithms for calibration and making the final images. And then we can finally get those beautiful radio telescope stuff. There's really fun things like Fourier transforms and like complex plane, like imaginary number stuff that is like hanging out in this. I think it's fun and like a puzzle. Other people hate it, but it's neat. So a lot of the initial calibration or the standard calibration is applied at the telescope in Chile or wherever the telescope is. There are multiple radio arrays in the world. I use like 4. It's just that one was my favorite. So you make that initial calibration at the telescope, and then they send you the data. And then on your computer, I can just barely get one observation to work on a laptop, like a really beefy, crazy, overpowered laptop. So normally we wind up using servers at universities to process this data. It takes a lot of effort because there's so much information coming from all of those 43 antennas, especially that telescope. It's very difficult data to handle. But we get the data. We get the data which is raw, and that's just because of a file size issue. So we don't get images delivered to us. we get raw data in like a machine-only readable format. We have to send it through some processing software to with some settings, because you can tweak the way you make images depending on what you actually want to find in it. In the data, it depends on your science goals, but there are little knobs to turn. So we turn our knobs, we send it through the algorithm, and then we finally get images out that we can do data analysis and science on. So that's how we get there.
That processing would take.
Okay, so I've been here 6 weeks, and when I started with a grad student ready to work with me. She has gotten through like 10% of it in 6 weeks, and she's been working really hard. So depending on the data set, depending on the complexity, and depending on the skill, she's also learning. So I would say properly processing one data set can probably take somewhere between a month if it's simple, or 6 months if it's really hard. Yeah.
Showed your picture of the Atacama Desert. You had 43 telescopes. It looks like someone took a bunch of dice and threw them across the, there's no, you would think there would be some sort of geometric pattern. I don't see one.
Actually, it's better if we don't have a geometric pattern. So basically what happens is all of these, when they're linked together, you have a collecting area power that's equivalent to like the whole area it covers. So they form like a synthetic dish, if you will. But the information can have a lot of noise and artifacts in it if they're not spaced in such a way that they cover like a lot of space in this Fourier transform of what you see on the sky. It gets complicated. But the point is, you get better image quality by having it in a pseudo-random pattern. Now, the exception to that is the VLA. The VLA is shaped like a Y. Sorry, the VLA is the Very Large Array in New Mexico. If you've seen Contact, a lot of you probably have. Jodie Foster's hanging out in front of the VLA. So that's 27 antennas shaped in a Y pattern. And the reason that all of that is still able to work is just because we've made huge advancements in our calibration. But when you're looking at the data, if you have a really bright star, we still see like spikes and artifacts. And we have algorithms to correct for that now, but that is an extra step that we have to account for. So, yeah, it's neat. Yeah, good question. Okay, so now that you're all radio astronomy experts, we're gonna move on to the science stuff. So first I'm gonna kind of go through like a general overview of the mind-boggling range of size scales that are involved in star formation. And then at the end, I'm gonna show you some stuff that I've been working on with my team. Okay, so we already talked about galaxies, so we can keep talking about galaxies more. So the largest size scale in the universe that I care about is galaxies, because stars don't really form that efficiently outside of galaxies, so I'm going to stop there. So what we normally think of when we think of a galaxy is, you know, some of those images from Hubble, right, with the beautiful spirals or maybe the nice ellipses. Well, there was this big FANG survey using the ALMA telescope in Chile, and I think they had 200 hours on the telescope, which is a lot. For reference, a typical project is about 10 hours. So they really trusted them on this one. And the results are amazing. So that was a really big gamble that paid off, investing that time in them and letting them pursue their science goals. So these are some pretty famous galaxies, some of them. And when we look at them in the radio, we actually see that these things are riddled with holes. They look like lace or doilies. Like, I'm pretty sure I saw some of these like on my grandma's table. Yeah, you have a question?
No, no, I was
Oh,
thinking they
okay.
all have the holes. See,
Yeah. So those holes, and these are again dust images. So we're looking at where your solid particles are hanging out. It normally means that this area is quite cold. So yeah, all of these holes are actually evidence of supernova. So these are where supernova blew up, blew a hole in the galaxy. And what we care about them because when they do that, they also sort of snowplow all of that dust into denser little subregions. And then if you have high enough density, you can trigger star formation. So supernova can help make stars. It's fun. And given that all of these galaxies have this lacy, holy pattern, we can probably say that supernova are really, really important in contributing to star formation, at least the second generation of stars. Yes?
Can you use the number of holes to age the galaxies, or do processes kind of remove the holes after a while?
There is actually a team in Spain that is working on characterizing, I think both age and like the supernova rate as it relates to the proportion of minerals that aren't hydrogen and helium in the galaxy. So they're kind of looking at both angles, but yeah, they're trying to figure out how do you pick the whole, what's not the whole, and they're trying to make it automated so that you're just not biased as a human. And but yeah, it's a hard question. It's a good question.
So I'm super interested in supernovae. Do you know if there's a way to distinguish between prolapse versus not prolapse supernovae just by the hole that it makes in those dust observations? Could be a method of classifying potentially.
Maybe. So mostly I work on small solar system scales. And this information has only been available for about a year. You should Google this survey and see what they're up to. Yeah. Okay, so galaxies, star formation starts to happen on large scales in galaxies because of the supernova snow plowing all this dust. And when it snow plows all that dust, oh, why are you weird? Don't be weird. Okay. So now you have all that dust. What's it going into? Well, it's going into molecular clouds. So what we saw previously, each of these like long wispy things, like that maybe that's a chunk or that's a chunk. Don't take my word for it. I don't work on galaxies. I don't work on this algorithm to find stuff like holes in mountains in these. But these things are very close to where we know there are these giant molecular clouds. So giant molecular clouds, as you might be able to guess, don't only have dust, they have gas molecules. So this is my favorite molecular cloud. This is the Perseus molecular cloud. This is a Spitzer Space Telescope photo. And some of the Spitzer CCDs were actually developed at U of R, and they have this photo in the hallway that my new office is in. So I like walked in and I'm like, oh, I'm home. I was excited. Also, I take my students down there all the time and I'm like, oh yeah, your program starts right here. Yours is over here. Okay, so the Perseus molecular cloud is about 6 degrees in size on the sky. And I know Perseus isn't a super popular constellation, but it's smack dab in the middle between Orion and Cassiopeia. And I found this cool little artwork. So if you don't know the Greek story behind Perseus, he's basically the Greek hero who slayed Medusa the monster and I don't know, saved all those wayward sailors that were crash landing on that island and doomed. And he's holding Medusa's head here. That's what that's supposed to be. Okay. So since I'm also an amateur astronomer, I like to do this kind of stuff. And when I do it at the universities, like in serious talks, they think I'm like, oh. But, okay, I think you'll trust me on this. So if you will hold out your hand at arm's length and make a fist, your fist, because most people's arms are in proportion to their hand size, your fist is covering about 10 degrees in the sky. Remember, I said that was only 6 degrees across. And guess what? There are 300 forming solar systems, little stars here. You're holding 300 little baby stars in your hand. That's fun. And it's actually all located in Perseus's foot. Okay. So, yeah, so within the molecular cloud, maybe I should go back briefly. Within the molecular cloud, you can see, again, it's not smooth. There's these stringy structures. So here's like something long and stringy. Just everything around here kind of reminds me of like egg drop soup, like when I get Chinese food. Like it's got that almost hair-like texture. So each one of those stringy hairs is called a filament. So filaments were not discovered in detail until the Herschel Space Telescope flew, which was in the mid, I don't know, like 2005 to 2009-ish, somewhere in there. I don't know the exact dates. I remember I was either in high school or undergrad when it went up, and in undergrad when it finished. Because the lifetime of these space telescopes, Herschel was a space telescope, when they're in infrared, you have to cool them because as they have sunlight that reflects onto them, they will heat up, and then it will give off infrared emission from the telescope itself. So then you have a lot of noise in your image. So you can only observe these for as long as you have, usually it's a helium coolant, like liquid helium, which has a temperature of 4 Kelvin. It's really cold and cool. But invisible light, I mean, they're barely there, right? It's because they're full of dust, they're super dense. There's still gas in there too. But everything's been sort of contracting and collapsing for a while now. But in radio light, it lights up like a Christmas tree. So once we discovered in the early 2000s that we had these filaments, that came around the time that a lot of our radio telescopes all around the world got a lot of really nice upgrades just because the advancement of technology. So this radio light image is one of the earlier ones from a telescope that lives down right next to ALMA, not quite the same telescope, but close. And when we got these improvements, and then we knew we should put from the infrared wavelengths that we should point to the filaments and observe them in radio, we start to see all, like even here, there's more wispy things within the wispy thing. It's like Russian nesting dolls. But here in particular, we see that there are 3 bright knots. And those are called cores. So a core is when, right, because nothing here is predetermined or predestined to fall into the protostars yet. There's no protostars that have formed. But when we get to the point where things are dense enough and compact enough, and they start to get rounder and rounder, that's because collapse is starting. And we define the edge of the core as where the material is gravitationally bound or not. So the stuff that is in a core is destined to make its way down to the protostar. Now, some of this other stuff might also make it there one day because sometimes there is movement and flows of gas along the filaments. that can feed the cores. But not guaranteed. There might be a supernova go off and everything's get destroyed anyway. So don't put your eggs all in one basket when you like protostars. They might not be around for long. Okay. So the core scale is kind of not well studied yet, or rather, it's well studied, but at low resolution. There's some stuff out there where people are trying, but if I showed you, I don't know, it's just not particularly visually appealing. It's a bit boring looking. But there's some information there. We pretty much know how they work. We just use a lot of analysis of the velocity patterns that we get from Doppler shifted light, that we can also detect with the radio telescopes. Oh yeah, I forgot. Oh, you guys have probably heard a lot from all the professors in town, right? So normally when people give talks, they're talking about facilities where you can either take an image or get a spectrum. Radio does both. You can't choose not to. You get it all at once. Ah. So anytime I'm showing you a radio image, think about a library card catalog, the old school ones, where each pixel, if you pull it out like the card catalog drawer, will have a lot of information contained in the spectra in there. Now you know why I can't fit anything on my laptop. Okay. So the pre-stellar core, it starts to collapse. And as we discussed earlier, there were the supernova. Supernova not only make the stuff denser, it makes all this stuff more turbulent. So that usually means that there's a little bit of rotation that will happen inside the core. And if you have even the teeniest amount of rotation, it will get amplified during collapse. So when that happens, to conserve angular momentum, the collapsing material flattens, and then some of the matter is actually ejected outwards, and that's called an outflow. So we discovered some of the super young protostars by their outflows first, because they were energetic and bright. It was only afterwards when they were like, why is there something where you have something that's red shifted here and blue shifted here, and there's nothing in the middle? That can't be right. That's when they turned their eyes to radio, and then they found the protostars. So some of the class of protostars that I study were really only discovered in around 1998, 1999. We call those class 0 because there was already a class 1 that was determined and found and characterized in the 80s and 90s. So if there was one younger, what are you gonna do? It's class 0. So I like those. Those are the just born protostars. And by just born, I mean, there's no fusion in the core of these stars yet. No sunshine. So everything that goes on here is still very cold. Oftentimes when we can measure the temperature of the disk, it's about 20 to 40 Kelvin. Super cold. So the general idea is that everything collapses, the rotation helps form that disk, and then the disk is where future planets will form, right? That's why the solar system is all in the same plane, because it also formed in a disk. And then as the protostars evolve, everything keeps collapsing. So this leftover material from what we call the envelope, which is the infalling material outside of the disk, there's still a little bit left and it starts to collapse. But then we start to see structure in the disks. They'll have rings or spirals, which might be related to planet formation. And then eventually all of your envelope dissipates. If you don't have any more infall, you won't have any more outflow. And then you will form a planet. Now, this is the only part we're really, really sure about because we have lab observations, right? We exist, so we know that that part's true. Okay, so here are some of those substructures. That's what we call all of these patterns in these disks. And this particular survey that I'm pulling these from, again, this is radio wavelength ALMA. These are images of dust disks. You have to build planets from tiny grains of dust. So that's why we care about the dust so much. So here's where all of your dust is. And we see that there's different varieties. So yeah, sometimes you get some that are looking pretty smooth, but more often than not in this survey, and they weren't targeting a particular type of structure. They were just pointing these at quasi-random protostars just to see what's out there. And we were stunned that there were so many rings and spirals because the rings and spirals can actually help make planets faster. Because if you have areas where you have less material, that means the density is less. That means you can actually convert that into like a pressure gradient in the disk, and you can help save those tiny dust particles from falling all the way into the protostar before they can turn into a planet. So these were like, bing, 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 bing. We got so excited. And it was great. And this happened when I was in grad school, and I was like, I want to do that. This is some other work by actually one of my friends and a former mentor, John Tobin. Now this is using two different wavelengths of data. So there's ALMA, which is roughly at 1 millimeter for this project. And it is shown in the bright yellow orangey color. And then the blue is VLA data. And what we actually see is, which traces a different wavelength of light. And what we actually see is that, one of them is more concentrated at the center than the other one. And like the pattern is consistent and clear. So what's going on here is that each wavelength of light traces a slightly different size of dust because the light that's coming off the dust, the wavelength is dependent on the size of the dust grain. So what it actually winds up turning out is that the larger dust particles are actually concentrated closer to the center versus further out in the disk. And that's because of drag forces. So larger dust particles have a larger surface area. So they experience more drag and they spiral in on faster timescales. So this might also help explain like why we have our rocky planets all in the interior of the solar system. Well, part of it might have been that we're concentrating our larger dust particles down there first. Yes.
Seeing these two sites here, can you also link observatories in different parts of the world? Same way, like make it super high resolution.
Yeah, which is what we did for the supermassive black hole image, right? It came out right around the time that there was a Nobel Prize for black holes for different projects, actually, but it doesn't matter. Yeah, so that was like a global one, and it was a huge effort. And the person that was in charge of doing that, her name is Katie Bowman. She was at the University of Michigan for undergrad when I was there, and she lived 2 doors down from me, like in the dorms. So that's just a really small world. Neither of us were radio astronomers back then. So oh, and just to show you where this stuff is in the sky, this is all in Orion. I've scaled this to be roughly the same size scale. And I just want to show you that this is the picture of the molecular cloud in the background. And then you could see the different disks here in the different wavelengths of light. And all of that is sort of hanging out over here on Orion's right side. No, just next time you check out Orion, remember that his right leg is full of protostars. About 356 to be exact. Okay, smallest size scale, planets. Surprise, surprise, this is a radio telescope image again. This little dot here is planet PDS 70C. So what we have is there's the central protostar, and it's got a little baby dust disk around it, and then a big gap, and then it's got one of those dust rings. But the planet lives in the gap. So what happens is the planet orbits the protostar, and much like Saturn's moons in the rings can cause ripples and wakes and little scallop shapes in the rings, same idea, much bigger scale going on here. So this planet has gone in, caused some of those rotational instabilities in the disk, and either accreted some of that material or pushed it into the rings. And when that happens, you might actually even be able to, if you let time play on for a little longer, although it won't happen in our lifetimes, we're talking like, wait a million years, that might trigger a second planet to form in the dust disk out here, because now this ring in the exterior part has also been compacted. So planets can help make more planets. Just get one, and then you're really in business. And we're also starting to do planets with JWST. So this is the first planet detected with JWST. I know it doesn't look super exciting, but they're still working out the kinks. They're fixing the calibration pipeline, and the teams are really cleaning up the data a lot. So I think when this is published for real and not just as a little preview, we're going to be in for a real treat with actually seeing some fine detail and really beautiful planets. Okay, so, yeah, oh yes.
What would be the density of those dust clouds?
About 1 particle per cubic centimeter.
Cubic centimeter?
Uh-huh.
Yeah.
Which is not very dense to us, but space-wise, that's pretty dense. Yeah, so now, section 3, last section. So we have people out there that study galaxies. There are people that study molecular clouds, and other people study filaments, and other people study cores, and other people study disks, and then finally other people study planets. But there's not been a ton of connecting the dots between all of these scales. And that's my favorite thing to work on for like the past 5 years. Okay, so we've got the cartoon, we've got some data, right? You've got the filaments in the cores collapse, they make disks. The disks develop structure that makes planets. We've got decent observations of the cores. We've got pretty good information about this older phase when we know we have a lot of structures. We know we have planets, we already exist. But what we're really missing is information here. I have not shown you a lot of information in this very youngest, just born protostar phase yet. So now you get to see it because it's my favorite, so I saved it for last. Okay, so, okay. First, when I'm coming up with an idea for a science project, my first thing I do is think about, where do we have gaps in information? Where do we have missing pieces? So here's the filament scale. This is somebody that I work with. This is in Perseus still, remember, my favorite cloud. Notice here, this scale bar is 30,000 AU. So you have a couple of protostars here, you have this long filament, and at the end of the filament, you have this lonely little protostar in the box. That's the filament scale. That came first. Then we have this scale. So that came next in 2018. So we'll come back to this. But when we looked at this protostar, we didn't exactly see a disk. It was kind of lumpy and weird, and we didn't really understand why in this particular source. So I and a friend that I had at the Max Planck Institute in Germany, which is where I did one of my postdoc positions. I was there for 4 years. It was super fun. Yes, it does. Oh, that was pointing at me. Okay, so you have this core envelope scale. We identified that we had missing information there that might help us figure out this mystery. Does this go away? Yes. So just to be clear, this is dust. This is dust. This is gas. And with gas, we can get Doppler motion. So we can figure out if stuff is infalling or rotating or just completely chaotic. And it doesn't matter that this is a really weird molecule whose name I can't pronounce. The fact is, it just has to be a molecule and it has to move. That's all it has to be. I don't care what it is. So what did we have here? We did not expect this. So there's this big thing here. And it's kind of pointing up in that direction. And this dust disk from earlier is kind of pointing up in that direction, like up towards that filament. So what we did is we modeled this data, and we fit the velocities of the Doppler motion that we extracted out of, each pixel is a spectrum, remember? So we get all this information. We extracted all that information. We ran it through a model of rotation plus infall towards a central mass. Pretty simple, and nicely, it worked. We'll come back to that. And what we actually wound up doing is naming this streamer, because we felt that because it was confirmation of infalling material that will land down near the protostar. Like, so this is all gravitationally bound material that will definitely end up in the protostar. Remember I said earlier that the filaments, that this material out here is not guaranteed to wind up in a protostar. It might get blown out. So because this has an end point, like a sink. Okay. I don't understand. Oh. If I don't move from there. This is wrong. Oh, it's probably not. Better not this one. The zoomers though. All right. That's okay. I used to do some public outreach in Texas and we used one of these, so I'm all set. I'll just have to talk slightly less with my hands, but that's okay. So, yes, so we gave these things a special name, not because, oh, we're special scientists, we need to have things that we name, but because there's a scientific reason and we need to identify these things that are definitely falling in, because it gives us an idea of how quickly these protostars gain mass. Because really, in the beginning, we don't know how quickly protostars gain mass from where, on what timescales, on what composition it's made out of, like what elements are in there, what molecules. There's a lot we still don't know. And there's a lot of variety in what we see, if we just look at each one at a time. I happen to like that everything's unique. It gives me a lot of job security. And this is my favorite. This is IRS 63. This is no longer in Perseus. This is in the Ophiuchus molecular cloud. So what we have here is another beautiful ring disc. That's great. This one has a very clear streamer, right? That previous one was kind of lumpy, like it wasn't like the nail in the coffin. But when we found the second one, we were like, yeah, this is a thing. And just so you know, I didn't go out meaning to observe this infalling structure. I was trying to understand the chemical composition of the disc down here. And instead, I found this thing by accident, and it's gorgeous. I love it. And this arrow here, that's not just like an annotation that I drew on in PowerPoint. That's a real streamline model, infalling streamline plotted. That's like, you know, there's uncertainties and parameters and error bars in that. That's science plotted without having the equations up there. But trust me, bro. And I'm extra excited about this for another reason. So you have this infalling streamer falling down, and it's connecting to this smooth gas disk, but the dust disk is smaller. Again, that's drag forces. Dust particles are larger than gas particles. But this is the youngest disk we know of with rings. It's so young, it breaks planet formation models. For a while, we used to think that the rings were caused only by the planets. This is a protostar that is so young, planets have not had time to form, according to planet formation models. So either that means the planet formation models are wrong, I don't think they're that wrong, or there are ways to make rings without having planets first. This has broken the chicken and the egg problem that we had. Yes?
How can you get what things to do? Where do you get that information?
Yeah, that's complicated. So because this isn't a main sequence star, we don't have a spectral type. There's no fusion, right? What we have to do is take measurements of their luminosities at many wavelengths, and then we do really complex modeling. So the uncertainties on the ages of these are kind of high, but they're still much younger than the other ones that we know of that have rings. And even if we're really generous with how old this might be, it still doesn't make the shortest planet formation model. It's pretty cool. So what we have here is a disk that is about to form planets. Like not next year, but you know, maybe in the next like 20,000 years or so. All the conditions are right. There is enough mass in the outer part of the disk to form multiple giant planet cores. Just the cores, because this is a dust image again, just dust. And then those things can accrete gas. You can also probably form terrestrial planets on the inside. Oops. Probably form terrestrial planets on the inside, but this yellow circle is actually kind of about the resolution of our telescope. And that's actually where the inner solar system lives. It's pretty cool because it is actually a solar system sized baby disk. We might be looking at how the solar system formed. Like this might be a twin. There's still some uncertainty of how our own solar system formed, but this might be it. And the fact that we actually see this big streamer these streamers, theoreticians, since I found this, have written papers where they show that in falling stuff, if it's asymmetric, so not falling in as a perfect sphere, but you have these streams, those can form rings. Cool. Yes.
Do these streamers ever create like shocks in the bus pylon again?
Yes, and it also shocks the disk on impact and heats it up, which changes the chemistry of the molecules available for planet formation. In particular, they release a lot of sulfur, and the astrochemists have had a hard time figuring out how to reconcile that the Earth has a lot of sulfur, but we aren't seeing it. There it is. Ta-da! Not bad for some like dumb luck thing that I found that I didn't mean to, right? It's pretty fun. You gotta keep an open mind about what's in your data.
Is that a one-off find right now today, or is there more examples?
That was the next slide. Yeah, so we're collecting more and more. This slide is now out of date. I think we're up to around 30. I'm planning large programs to find some. But first off, let's just look at the variety and the awesomeness that we have. Okay, so there's my friend. There's that first one that we found. When we looked back through the data, we went back to 2000, because that's roughly when the telescope started having the capabilities to actually detect these things. We found some in old data, already published data, right there. We're pretty sure that that's something that's falling in. This is a protostar that has 4 of them that are coming in, all from different directions. This is one from a PhD student that I worked with in Germany. It's great. And this one has a lot of those shocks, very sulfury, very shocky, all right at the head of where the streamer is like punching the disk. This is HL tau. It has a huge series of rings with it. I think it's got like over 15 rings. So there's a lot, something's going on in here for sure. And it's got this stubby little tail that sticks out of it. And I could go on. And I also just want to point out that over here, these are the younger sources that I study, these 6 on this side of the plot. And then these ones are a little bit older. They're nice, they're just not my favorites. And these are the ones that are about to go main sequence. And they are still collecting material in this asymmetric way through the streamers. Also, these streamers are found in a bajillion different molecules like HC3N, C18O, H2CO+, 12CO. Here's some in dust, N2H+, which only exists in space. The fun thing about having friends that are astrochemists is you learn all about these things that they can't actually make on Earth. But yeah, so to answer your question, we're fine. Okay. Yes.
One more question. When you say asymmetric streamers, does that mean, I guess that like the streamers coming in off axis from the plane of the photodisk, or is it? I guess my question is, what does asymmetric mean?
Oh, it just means that the total infall is not from a sphere. Like there's not perfect plane symmetry. You can still collect from a midplane as long as it's only from one direction and not perfectly counterbalanced from the other, because then you impose symmetry again. I mean, all of space is asymmetric, so, you know, we got to move on from these symmetric models anyway. Isn't that what AI is for? Okay, almost to the end here. So this is something I'm really proud of. This is the Prodigy survey. So it's a very forced acronym. Protostars and disks, global evolution. So my boss, Paula Caselli, gave me the opportunity to completely drive this bus. I'm in charge, even though for academic political reasons, I could not have my name on it. This is my baby. So I'm studying 32 protostars in the Perseus molecular cloud. And we are finding so many streamers. Of the data we've collected so far, there are obvious streamers in 60% of the sources that we see. So that's fine. I don't have to be around every protostar, but it's not 10%. It's not a minority. There's a lot. It's important, and we need to keep these in mind. Okay. So with that, I kind of want to update this image that we had earlier, right? Back to the asymmetries. So the top part was what we thought. It was a good start. I'm not saying that the old work is bad. They were doing what they could. It was great, but it's time to build on their shoulders. So what we need to do to the old model to make some progress is we have to throw away some symmetry, starting with the prestellar core. Prestellar core is just, they're lumpy and they're weird. And I know there are some that are egg-shaped, but I've never seen a perfect sphere. I've never seen a perfect sphere in space. Like, have any of you ever seen a round cloud? Right? Yeah. Exactly. But round cloud is often our base starting assumption. It's time to get a little more complex. Then in the very youngest baby phase that I love so much, not only did we find out from my work that we have infalling streamers, we also know that those ring disks that are so friendly to making planets, they're also in this phase. So we've got to bump that to earlier timescales, which means that maybe by the time you get to the older phase where we know there are tons of ring disks, and we know there are planets. Remember I showed you PDS 70C, that's in this phase. That's while there is still some residual infall still occurring. That might mean you could change the atmospheres of your planets, like their composition, just from the material coming from the outside cloud. It's like an extra spice at the end of making a recipe. End result is still the same because we're still here. All right. And with that, I'll just leave you my summary, but everything's connected. I really like radio astronomy. Thank you.
Talk about the role of supernovae and transformation.
So there was still, after the Big Bang, there was a ton of hydrogen and helium. So eventually, as the universe was expanding, there's always quote noise in the universe. So there were these little inconsistencies, and that led to overdensities, that led to stars. We think the first stars formed very differently, maybe on much longer timescales, because there wasn't a preformed molecular cloud that they could have their nursery in. So it's a little different, but there's still an initial collapse of gas that was made right after the Big Bang. That forms a big star. We don't quite know the physics of those first stars. They're weird and different, but then they blow up, and then we get all of our nice elements that we use to make the rest of them.
So should I be thinking of molecular clouds as being full of filament structure?
Yes.
And at the end, just as when you finally get to the stage where you have isolated planets, is it that they kind of drain the nearby material from the filament or streamer? Or is it that the ignition, if you will, of the star, where it's where fusion's happening and it's clearing out material, does that cut off the filament?
So by the time fusion occurs, the local area has mostly been cleared out, but there's still those little residuals left. So outflows from those early stages can absolutely still continue to clear material if they're still in fall. But you're right that when there's fusion that ignites, you know, we have solar winds. We're about to get hit by some stuff today, right? Yeah, so the solar winds will push out, and I mean, we essentially like make a bubble in our own universe. But by the time they're doing that, it's just like the last bits, the dregs.
And one other quick question. Your one image you showed a filament where you had 3 cores that appeared to be close to each other.
Yeah.
Has anyone done any modeling on how those might interact in terms of material?
Yeah.
What happened?
So I'm not sure about those specific cores, but in general, cores can do a lot of cool stuff. They can sort of slowly merge, but they can also smash into each other. And that can sometimes like form a slightly larger star, but then it's pretty chaotic, and that might actually help produce multiple streamers. There's a team in Japan that's working on that now, and they're saying that dense core collisions can cause streamers. Cool.
In a recent James Webb Telescope image, there was a shot of these things they call jumbos, which are pairs of Jupiter mass planets that are forming the random magnet. What might possibly be related to this? Maybe escaping objects or something like that?
They could be escaping objects, but it's really hard for binary objects to escape. So what this probably is a failed binary star system. They just didn't collect enough material to do fusion, so they sit there as they are. They're really hard to detect, but some star and planet formation models predict there should be tons of them. We just don't have sensitive enough instruments to find them, which is why we were all so excited about those.
Your models does multiple star systems happen?
So the question was, where in the models do multiple star systems happen? So I didn't actually highlight it here, but let's go back, we'll find our friend. This first one here is actually a binary system down at the bottom. Like within that one star at the teeny tiniest scales, there's a binary there. Binaries actually form pretty easily as long as you let asymmetry happen in the models. So as soon as you introduce turbulence or magnetic fields or a warp, it's pretty easy to form binary systems, which is why, you know, like half of the stars that we know of are in binaries. So it's cool. They're all over, everywhere.
Hi, well, one thing I noticed is that you seem to have isotopes noted in each of these images. How does the isotope make a difference that that is A13C? Sometimes 12, other times 14, other times. I mean, don't you get them all at once?
Well, we don't, because the molecular transition frequencies for each isotope is different, and sometimes they're not observable together. We often do have 12 CO
13 CO and C18O all together, because those are super important. And they're important because they have different abundancies. So 13C is more rare than 12C. And C18O is more rare than those. So and since the frequencies are different, this means that even if you have so much 12CO that it's optically thick in the radio, yes, optically thick in the radio, 12COs you can give up on a lot of times in the very young stages. But 13CO might work. And if you get to the youngest stages, you want C18O because there's fewer molecules and the photons can actually escape faster, just because there's so few of them, even though the density is really high. So it's like a little chemistry, it's a little astronomy. It's cool.
Any more questions from the room? I mean, online? In masters, or, I mean, like, are so many people we failed to start, maybe all of you have enough masters done?
Okay, so the question is, can we get masses for these protostars? Are any of them failed Jupiters maybe? And will some of them actually become stars? So because there's no fusion, it's actually really hard to get masses. That's what I have literally 5 students working on right now. And what they do is they use rotation in the disk and the velocities there to measure the central protostar mass. And then we can try to make estimates of how much material is falling in through streamers, and then subtract the material ejected in the outflow in the whole region to try to figure out what the quote total mass budget of the system is. So it's a lot of work. We're getting there, and I don't know, check back in 5 years. I might have an answer.
The rogue planets, if you have enough and they continue in the universe and they get to first, where do they come from?
Yeah, so there are multiple versions of what might happen because it's very hard to observe them right now. So it's hard to rule out predictions. There's multiple predictions out there. Some of the rogue planets might be ejected from solar systems with stars. Other rogue planets might form in the same way a star does, and they just had much less mass available. So hard to tell.
So I'm curious if you know of any model that predicts the size of rogue planets and their dispersion, or are they just stand alone?
That's a good question. I don't know. I gotta go Google that now. I'm curious.
You described radio astronomy as being both image and spectral. And so how many, let's call it channels, how many channels would there typically be per pixel? So how are you breaking up the spectral component?
Either 1040 or 2048 are common channel numbers. Yeah, a lot. Typically that translates to a velocity resolution of 0.2 kilometers per second, which is really nice. And that's how we can do all this modeling.
That's something.
Yeah.
I know, I read that, see this mini moon that we have right now. We need a 30-inch telescope to see it in the optical and either CCD or CMOS, but, what about the radio?
I mean, the shorter answer is yes. It would depend on how long you have to observe it. Because you might just have to track it and integrate to get enough signal. So you might need like a longer time range, but you can see relatively cool stuff with that. And I do know of some asteroid and trans-Neptunian object people who use radio telescopes to track their objects. It's cool. Everything's cool, you guys.
Well, thanks, Dominique, again.
Talk? So we do have this tradition that we kind of got away from during the pandemic that we're still trying to reboot if people have time. When we go to Applebee's, just to, have a drink or an appetizer and socialize after our meeting. So everyone's invited to go to Applebee's and hang out for as long as you want to. All right. Yeah. Which one is it? The one on West Henrietta Road. All right. All right. All right. Thanks, everyone.